So, good afternoon. My name is Francisco, and I'm from TPRC, it's Thermoplastic Composites Research Center. And mainly what we do is thermoplastic composites, and mainly what we do is processing them. And okay, the title of my presentation is Woven Fabric Composite, Can We Build It? So what I would like to present today, what is our problem? So mainly we would like to characterize the toughness of these materials, but we will know how to do it properly. So basically we select two different testing techniques, and we'll show you the results that we have with them, and at the end I just will summarize what we saw. So basically, what is the material in which we are interested in? So it's a thermoplastic composite, mainly carbon peak. In this case it's a woven fabric, fine hardness. And the stacking sequence that we use in particular for this test is that one. And mainly so the direction of the crack and propagation direction in which we were interested in was with the crack propagation in the same direction of the main direction of the fibers. So how can we characterize the mechanical or the toughness of these materials? So we went to the standards. We have many standards for fracture toughness, but mainly for UD materials. But what is there for woven fabrics? There is not much. So okay, we try to use DCV testing and see what happens there. So we try to test our materials with the DCV, and oops, something goes wrong there. So basically what we have is really unstable crack propagation or sticky slip behavior, and it's quite difficult to analyze this data if you use the standard for UD materials. And so basically we try to look for other standards, for instance for adhesives. This is quite common. And they say, okay, you should take the load peaks where your stable crack propagation starts, or reinitiation sometimes it's called, and we will try to calculate G1C in those points. But what we found is really high scatter. So if we try to use this value to improve our process, it's quite difficult to see whether we are doing something better or not. So is there any other alternative to use or to measure the G1C or G of these woven fabrics? So we were looking in literature, and we found this paper from Kawashita. He tried to measure the toughness using a MANDREL test. In his case, the system was quite more complex than ours. He was peeling a metallic part from an adhesive. So there was a lot of plastic deformations, but mainly if you take out all the plastic deformations, you end up with really simple equation to calculate G1C, and the only thing you need is mainly a MANDREL to make conform your material to it, so in such a way when you apply the peel force you don't break the peeling arm, and you need an alignment force to make this peel arm to conform to the MANDREL. Which is the problem of this system is, okay, you're measuring the alignment force, you're measuring the peeling force, everything that happens in between, so any dissipation energy you will have in between these two measurements will affect your measurements. So mainly friction. And if when we release or when we generate our crack, we release as well residual stresses or thermal stresses, it will be in that measurement. So the work of Kawashita was designed for another system, but okay, we will try to find which were different parameters that will match for our system. So mainly we changed the cross-cut speed, we changed the sample width, trying to match the sample's width of the DCV test, and we kept the alignment force constant. Anyway, this is some other variable that we could change in the future. So this is the test itself. So at the beginning we were really happy So the pin arm was conforming the mandrel. You can see a quite stable crack propagation, at least if you see it from this video. So we were happy, we said, okay, this is working. Then if we go to see the force displacement, what we can see is the force is really going up and down, up and down. So something is happening there. And by the way, we performed the test two times, when it was still bonded, and a second time just to check what was the friction in the system. And what we observed is the bottom line, so that's the friction of the system, so it's really small. So we will take it into account, but it's almost negligible. But what was going on there? So why we have these high forces going up and down? So what happened? So at the beginning of our test, we have the pin arm that is really conforming to the mandrel, and then as soon as the crosshead keeps moving, what we have is the pin arm stops to conform directly to the mandrel, and it doesn't propagate until we generate enough energy in that system. So at the end, what we end up is again with really unstable crack propagation, or again sticky slip behavior. So again, we use the same system to calculate the G1C. So we took only the peak loads, and we tried to calculate the G1C with that one. But the main difference we can see now is, okay, now we have many values. So in the DCB, barely we have 5 points per test. Now here we have something around 40. So, okay, from a statistical point of view, this should be much better, or at least what so in the fracture surface, what we can see again is the same thing. So if we try to find where the cracks start. In DCB test, we can see one line and then really stable crack propagation. While when we use mandrel build test, we can see these many starting and resting points. So the average distance between this starting and so between each initiation point in a DCB test was around 20 millimeters, while in a mandrel build test was around 1 millimeter. That means that we can generate much more data for smaller quantity of material. Then when we try to see how is the scatter in this data, what we can see is mandrel build test is not doing much better than what is doing DCB. We have really big scatter, but what we have is anyway, even if mandrel build test it has a mixed mode, mostly mode 1, the G results or G values that we were able to measure were in line with the DCB. So but the problem again is how we go from. The other point is our G values are, even if we have a big scatter in the values, the average values are always in line. So this is another big problem that we have. We don't know how to analyze properly this data. So we have a lot of scatter for a single coupon or for a single specimen, but then when we try to go to sample size, then we average the values and we have really small scatter. So the conclusion of the work of, okay, mandrel build test work, we can build our own fabrics and it doesn't break while we test them. And the results that we have are really in line with what we can have with DCB test. Thank you.